Hello everyone, and a huge welcome to today's explainer for our software engineering course. It is absolutely great to have you here. Today, we're zeroing in on Chapter 10, specifically Section 10.5, which is all about formal methods and system dependability. We'll also be comprehensively wrapping up the Chapter 10 key points. So if you're gearing up for your upcoming assessments, you are exactly in the right place. We're going to break this material down step by step to make sure you have a really solid practical understanding of these crucial concepts.
Okay, let's dive into this. Here is our roadmap for the session. We'll kick things off with an introduction to formal methods, then explore the two main approaches. From there, we'll look at why the industry actually resists them. After that, we'll summarize the Chapter 10 key points and wrap everything up with a dedicated exam focus.
Starting with Part 1, an introduction to formal methods.
Now, in the world of highly critical systems, think about aviation software, medical devices, or railway controls. The stakes are just too high for guesswork. We are moving far away from just writing a program and hoping for the best to a place where we actually prove it works mathematically. That is exactly where formal methods come in. So, let's define the term clearly. Formal methods are mathematical approaches to software development where a strict formal mathematical model of the software is defined and analyzed. What does that mean in plain English? It means instead of an engineer just sitting down and typing out lines of code, they first build a strict mathematical model. They use formal logic and mathematics to officially prove that a program perfectly matches its original specification. It is literally the most precise way to specify a system, completely stripping away the ambiguity you naturally get when you write requirements in everyday natural language.
Because we're using these robust mathematical models, formal methods are incredibly effective at dodging two specific classes of errors. The first, specification and design errors, including those pesky omissions. You see, putting together a formal specification forces you to do an incredibly detailed analysis of the system requirements. This deep dive catches errors and misrequirements super early on, long before a single line of a program is even written. And as we all know in software engineering, fixing an error during the requirements phase is massively cheaper than trying to patch it after deployment. The second class it avoids is inconsistencies between a specification and a program. Since the whole process is rooted in maths, you can systematically prove that the final code does exactly what the specification demands, and absolutely nothing else.
Moving on to Section 2, let's look at the two main approaches to formal methods. You definitely want to pay close attention and make sure you can distinguish between these two.
First step is refinement-based development. With this approach, you start with your mathematical specification and you transform it step by step into software code. Because you are relying on trusted, mathematically verified transformations at every single step, you can be totally confident that the resulting program is flawless and aligns perfectly with the spec. The second approach is model checking. Here, you build what's called a formal extended finite state model of the system. Then you use a specialized software tool, a model checker, to exhaustively analyze every single possible state to prove that safety properties always hold true. Think of model checking kind of like navigating a giant, complex maze. The model checker systematically maps out every single turn, every corridor, and every dead end exhaustively just to guarantee there's no possible path where the system could get stuck in a dangerous state, like a deadlock.
And this brilliantly illustrates a real-world application of refinement-based development. The software for the Paris metro system was actually built using a formal language called B. Because the developers used specification refinement, literally transforming the mathematics step by step into code, they trusted the transformation so much that they completely bypassed software component testing. No way, right? They mathematically proved the components were correct, meaning they only had to run system tests at the very end. It's a truly phenomenal success story for formal methods.
But looking at a massive success like that naturally leads us to a really important question. If formal methods can generate practically flawless programs, why does the vast majority of the software industry completely avoid them? It sounds like a magic bullet, doesn't it? Well, we need to clear up this common misconception that formal methods just magically guarantee a flawless real-world system without any trade-offs. It's time to pivot and look at the harsh reality of why industry adoption remains so incredibly rare.
Which brings us to Section 3, industry resistance to adoption.
Despite the theoretical brilliance of catching errors early and proving code is correct, there are severe practical limitations and business hurdles when you try to implement formal methods in the real world. There are 6 major reasons for this resistance. First off, clients and domain experts simply cannot read complex mathematics. If a client can't read the specification, they have no way to verify if it actually represents their business needs. Second, the massive upfront costs are incredibly hard to justify to management because the return on investment is just too difficult to quantify. Third, the reality is most software engineers simply lack the deep training in formal logic and mathematics needed to write these specs. Fourth, these methods are notoriously difficult to scale. When they are used, it's usually just for small, highly critical kernel software, not massive sprawling systems. Fifth, tool support is quite limited, often open source, and honestly can be pretty poor because the commercial market for these tools is tiny. And finally, number 6, formal methods require a very strict, plan-based approach, which makes them fundamentally incompatible with the rapid, incremental, agile development methods that most of the industry relies on today.
Okay, that brings us to Section 4. Now that we've covered the realities of formal methods, we are moving into a comprehensive summary of the key points for the entirety of Chapter 10.
This recap is absolutely crucial for your exam preparation, so let's review the core foundations of system dependability. This entire chapter has revolved around how dependable a computer system is, which at its core reflects the degree of trust a user has in that system. There are 5 principal dimensions here. Availability, which is the probability the system is up and running when requested. Reliability, the probability it correctly delivers expected services over time. Safety, ensuring the system won't cause damage to people or the environment. Security, the system's ability to fend off accidental or deliberate intrusions. And finally, resilience, how well the system can maintain its critical services and recover during a major disruptive event, like a cyber attack. Collectively, it's these 5 properties working together that build total user trust.
Now, what's really interesting about this next concept is how it frames where our software actually lives. Software does not exist in a vacuum. It exists within a socio-technical system. That means it includes the equipment hardware, the operating system, the application software itself, but crucially, it also loops in the business processes, the people, the society, and the organizations. All these layers are interacting constantly. You just cannot build a dependable system by only staring at the code. You have to understand the human operators using it and the organizational policies governing the whole shebang.
To secure these complex socio-technical systems, we lean on a few key architectural and procedural techniques. We have redundancy and diversity. This is how we structurally protect a system from going down. Redundancy means having backup components ready to go, while diversity means using varied software or hardware so they don't all crash from the exact same bug. Working together, they eliminate single points of failure. Then, on the other side, we have dependable processes. This is all about how we actually build the software in the first place. By sticking to auditable, repeatable, and explicitly defined workflows, we actively minimize the number of faults that slip into the program during development.
Which brings us to our final section, the exam focus and conclusion.
All right, I need everyone to pay close attention here, because this is your mandatory exam knowledge for this module. First, you absolutely must be able to clearly distinguish between refinement-based development and model checking. Remember, refinement is a step-by-step mathematical transformation into code, whereas model checking is the exhaustive analysis of a state model to prove safety. Second, you must be able to list and briefly explain at least 3 of the 6 reasons why the software industry pushes back against adopting formal methods. Think about the lack of mathematics training, those high upfront costs, or how it clashes with Agile. Get these specific concepts firmly memorized, and you'll be perfectly prepared for the test.
Before we finish up, I want to leave you with a provocative thought. Let's say you do use formal methods and you manage to prove your software code is mathematically flawless, but then the physical hardware it runs on fails or a human operator makes a critical data entry mistake. Can we truly call that entire system reliable? It brings us right back to that socio-technical stack. Perfection in code does not always mean perfection in the messy real world. I want to congratulate you on mastering the foundations of system dependability today. You've done excellent work. Keep this broader socio-technical perspective in mind, because in our next explainer, we'll be diving into Chapter 11, where we explore reliability engineering in even greater detail. Until then, happy studying.